I will be explaining you in this video theorem 26.7. Here you can see the statement of this theorem. The product of finitely many compact spaces is compact. Okay, so it means you have to take so many compact spaces and the product, okay, you will take so many compact spaces, and what you have to prove is the product of that compact space is also compact. That is what we have to prove. To prove this, what you will do is, first you will take two compact spaces and you will say product of that two compact spaces is compact. After that, by induction, you will say this is true for this is true for finitely many compact space also. That is how you will conclude the proof of this theorem. So here what we will do is, let us follow my notes to learn further. Okay, so as I told you earlier, you have to write first to prove the product of, you have to take two compact spaces and you are going to say the product of that two compact spaces is compact. That is what you are going to do now. So first, step 1, after writing first to prove this line, what you have to do is, you have to prove tube lemma. Also, step 1, put step 1, and in the step 1 you have to write the statement of the tube lemma and you have to write the proof of the tube lemma also within this theorem. Okay, so already this tube lemma is a very important theorem, so you have to use this tube lemma. You are using the proof and statement of this tube lemma entirely, you are using in this theorem also, within this proof also. So imagine how important tube lemma is. Okay, if you learn it once, you can use it for two theorems, right? Yeah. Okay, so here in the step 1 you have to write the tube lemma, and it means you have to write the statement, also you have to write the proof also. Okay, so in the step 2 you are proving the main thing, that what in the statement they are asking us to prove. So here in the step 2, as I told you are taking two compact spaces, that is x and y. Okay, let x and y be two compact spaces. That is how you have to write the sentence. To prove, what you have to prove, the product of these two compact spaces is compact. That is what we have to prove, right? So write it. To prove x cross y is a compact space, or x cross y is compact. Okay, so to prove if you want to say this is compact, what we will do, by the definition of compact, you will do something. That is, from this you are going to say this is compact, right? So from this you will take an open covering, that is script A, and by taking that, at the end of the proof, what you will say is, within this script A you will take a collection, finite subcollection, collection of elements from this open covering, and you will say that finite subcollection is also covering this x cross y. Then you can say this x cross y is compact. That is what the concept that you will come to know from the definition of compact. Okay, so here also we are going to do the same thing. You are taking an open covering from this x cross y. Let script A be an open covering of this. Okay, and then what you are doing in between, to say that in between you will do so many things. You are going to apply tube lemma, so that you have to bring the proof in that format, right? If you want to use the tube lemma, you have to bring this first. You have to bring these things in the proof first. After bringing these only, this is the statement of tube lemma. Okay, after bringing these things in that proof only, you can apply the tube lemma. If these conditions are there, then you can apply this, right? So that is what you are going to bring these things in that proof. That is what your next thing that you are going to do in that proof. Why you are doing that? To apply tube lemma. Okay, so here what you are doing, you are taking a slice. From where you are taking a slice? Our x cross y. From x cross y you are taking a slice, that is this. The slice is compact. Okay, how you can say the slice is compact? Because the slice is from x cross y. You know that x is compact, y is also compact. Therefore the slice you have chosen from this x cross y will be also compact. Okay, so that is why the slice of this is the slice of this, okay, is compact. Now you know that you told it is compact. So there will be an open covering script A, and within that open covering you will take a finite subcollection, and that subcollection will also cover this slice, right? That is what the definition of compact. To say this is compact, that is what the definition. So that same thing you are doing here also. You are taking a subcollection from script A and you are saying the subcollection is also covering this slice, okay, because this is compact now, right? So that is why in the next line you will write, hence it means what? The slice is covered by finitely many element this of script A. Okay, that is why you are writing this sentence. Okay, in the next line what you are doing is this is the collection, right? This is the some of the elements, collection of elements that you have took from this script A. Script A is an open covering, okay? So from this you are taking some elements. You said that this slice is, it is covered by this, okay? The slice is covered by this, okay? So using that you can say, then when you find the union of these elements of script A, A1 union, A2 union, etc., A union AM, this is an open set. Okay, this is an open set containing X0 cross Y, because it is covering, right? Okay, that is why you are saying open set containing X0 cross Y. The reason is because you are covering this slice. This elements, this collection is covering this slice. So it means covering this slice. If your slice is, you are having slice, sorry, capital Y, you are having slice, you are covering this slice with this collection. It means what? This slice is present inside this covering, right? So that is what you will use here. Then n equal to this is an open set containing this slice. Okay, that is how you are writing this union, A1 union, you are choosing it as n, okay? You are telling n equal to this value is an open set containing this slice, okay? Because why you are saying containing? Because the slice is covered by this collection. That is why you are saying this containing this. It means this present inside this union. That is X0 cross Y. The same thing you are writing in this format, X0 cross Y contained in n. Okay. Now you got a slice. That slice is present inside an open set n. Then you can use tube lemma. Okay, that is what you will have in the statement of the tube lemma. Here you have a slice. That slice is present inside the open set n, so that you can use what? Tube lemma. That is why you are using tube lemma here. So by step 1, what is our step 1? Step 1 is our tube lemma, right? So you are using tube lemma. If a slice present inside an open set n, then n contains some tube. That is what tube lemma statement, right? So you are writing n contains some tube. This is W cross Y. Where you can find the tube? By tube lemma. Above the slice, that is what you are writing, above the slice X0 cross Y, where you know that in the statement you have learned it, where W is the neighborhood of X0. This X0 belongs to where? Capital X. Just rewriting the statement of tube lemma. Then from this you can say this W cross Y is covered by this of script A. You already have n is equal to union of these values, right? So here what you are writing is, you know that from that statement the tube present inside n, right? Here you have chosen n equal to union of these elements. So that is why by using all these things you are writing thus W cross Y. It means this tube is covered by n, right? See here what is our n? A1 union, A2 union, A3 union, right? So you are not writing union here, you are just writing that collection. W cross Y is, that is, this tube is covered by this this collection. This is the finite subcollection of what? Script A, open covering, right? So that is what you are writing. Now for each x belongs to x, that is, for every element present in capital X, this is an element from capital X, right? Similarly, for any element present inside capital X, you can find a neighborhood like this. You are writing it as, in general, you are writing it as Wx of what? That element x, such that Wx cross y, okay, that neighborhood, you are writing in general, okay, Wx cross y is covered by this collection, covered by this of script A. That is what you have to write. And then you are, if you for each element, if you get a neighborhood like that and neighborhood like this, okay, for each element of x belongs to x, you will get so many neighborhoods like that, okay. Then the collection of you will have so many neighborhoods. Now the collection of neighborhoods are denoted as Wx, the collection of all neighborhoods Wx, okay. You are having so many neighborhoods, the collection of all neighborhoods will form an open covering of what? Capital X, okay. That is how you will write. All the collection of neighborhoods will form an open covering of what? Capital X, because you are taking neighborhood for the points present in capital X. Is that clear? Can you follow me? Now, since X is compact, in the first line you have wrote X is compact, X and Y are compact, right? You are using here since X is compact, what you know, if you here X is compact, you confirmed it is compact. It means it is satisfying the condition of what? It is satisfying the definition of compact. What is our definition? If you take an open covering from this capital X, that open covering will have a finite subcollection that will also cover this capital X. That is what the definition, right? The same thing you are writing. Since X is compact, there is a finite subcollection this covering what? Capital X. Here you are not talking about open covering you are choosing. You are just writing what you are going to get from the definition. You are getting a finite subcollection this. That finite subcollection will cover what? This capital X. Is that clear? Now the union of tubes. Here you have talked about the neighborhoods. Neighborhoods means only this Wx in general, you can say only Wx. This is a neighborhood. When you write it with y, that is Wx cross y, means you are talking about the tube, okay. So here you will have so many tubes also, okay. Here the collection is covering tube, right? So you will get so many tubes also. Here you are having so many collection of neighborhoods. That neighborhood is covering is an open covering of capital X. You finished writing it. Similarly, you will get the union of tubes also. You will get a collection of tubes also. Now you are writing for tube. The union of tubes. You will get so many tubes like this. And this tubes is covered by finally many elements of script A. This tube E is covered by the many elements of what? Our open covering script A. Okay, that is what you are writing. Learn it with like a story. Okay, this tubes also covered with what? Open covering script A. Neighborhood will become what? The collection of neighborhoods will become the open covering of capital X. Can you understand? Okay, since each Wi cross y, it means in general you are writing. We are talking about tube, okay. Each tube is covered by finitely many of the elements of script A. The same sentence you are writing, but in general you are writing. Since it is happening, since each tube is covered by finitely many elements of script A, you can say our X cross Y is covered by finitely many of the script A. Each tube is covered by what? Finitely many of the elements of script A, right? Therefore, this X cross Y, our X cross Y we have, right? That is also covered by finitely many elements of the script A. So finally you brought it. In the first line you are taking script A is an open covering of X cross Y. In the end you are bringing that script A is having finite subcollection that is also covering X cross Y. You have brought it. Okay, it's a finitely many elements of script here that is covering x cross y. So you have brought the definition of compact here. So therefore you can say this x cross y is compact. So you proved it for two compact spaces. So by induction you can prove for finitely many compact spaces also. So that is what you are having no proof for it. You are just writing by induction the product of finitely many spaces compact. Therefore by induction you write the sentence, hence the proof.